Stopping distance problem. This is problem number 4 from lesson 1-1 problem set. So the distance of your car takes to stop depends on how fast you are going when you apply the brakes. You may recall from driver's education that it takes more than twice the distance to stop your car if you double your speed. Letter A, sketch a reasonable graph showing your stopping distance as a function of speed. And letter B, what is a reasonable domain for this function? So first of all, we have to label our x and y. So this is our x-axis and this is our y-axis. This x-axis, it should be x-axis. Okay, this x-axis represents your, what does it represent? Your speed, okay? The speed. And this y-axis here represents your stopping distance. Stopping distance. Okay. Let me make it better. Stopping distance. Is stopping distance. Okay. Now, for a certain speed, if you have a slower speed, of course, your stopping distance or your braking distance would also be low. Okay? So, for example, we have, let's say, 1 meter here. 1 meter. Okay? Stopping distance. If our speed is about, let's say, 4 kilometers per hour. Let's say our speed is kph and our distance is in meters. So at the speed of 4 kph, let's say our stopping distance is 1 meter. Now as you can see, think about it. If you have a car, if you increase the speed, your stopping distance would also increase. That's why you can see the points here. They are plotted. Okay, they're already here. They are already here. But this is just, these points are just assumptions. These points are just assertions indeed. Okay, about the relationship of the speed and stopping distance. So at this portion, okay, let's repeat that. So this portion, you get this part. You get this part. Okay, this one and this one. This one, let's use the grapher. Okay, you can see that I'm not okay, let's use the grapher for more accurate graphing. So we have this and so on. For this one, we go to a y coordinate. For this x coordinate, we have a y coordinate. And for this, we get this. For this, we get this. And for this, we get this. Okay. So at a speed of, let's say, 8 kilometer per hour, which is about let's say 10 instead of 8. So 10 kph. And then maybe this is the maximum at let's say 100 kph. That's the limit of your car speed. So let's say this is about 500 meters. So as you can see, as your speed rises, as you increase the speed of your car, the braking distance or the stopping distance, in other terms, the stopping distance would also equal to a corresponding exponential. It increases rapidly, the stopping distance increases rapidly as speed becomes greater and greater. Okay? So that will be my illustration of the relationship of the stopping distance and the car speed. Okay, taking it as a personal observation or just an assertion. So let us try to connect, or let's connect the dots. Let's connect the points or the dots. So we will have from here, I will try a better color. From here, it shouldn't be less than 0. It should not go lower than the y is equal to 0. Okay. So I am connecting the points. I'm connecting now the points. Okay. I'm connecting the points now, and I'm tracing it using a highlighter. Okay. So notice that we are getting a graph here which is exponential in nature, or which rises increasingly as speed goes greater, then our stopping distance also goes greater. Okay, with certain points of relations. You have these points, this point, 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 and the origin. Okay, so sketch a reasonable graph. So this is our graph as a function of speed. As speed goes greater, our stopping distance goes greater also. So this is a relationship, but you can see that this is not linear. This is not straight. It's curved, because for a certain speed, the stopping distance will be different, and they are not linear. Such as if your speed is 1, then your stopping distance cannot be equal to 1. That's what I meant by linear. So this case is exponential. It is somewhere like for a certain x, for a certain speed, okay, at S1, you will have a corresponding braking distance of, at x1 rather, you will have a corresponding braking distance of y1, and x2, y2. So this will be the corresponding graph. Okay, letter B, what is a reasonable domain for this function? For this function, we could see that our domain is from our x would be from 0 to the speed limit. Speed limit. This is our domain. Okay? Now for the range, our 0 or our y would be equal to 0 but less than the value of the stopping distance, let's say y at a maximum speed limit, or the speed limit or the maximum speed. Okay, or let's make it congruent to the y, to the x. So this is y at speed limit. This will be our range. This one will be our range. Okay, now we are going to present some of the illustrations taken from the internet. So I have taken this illustration from one of the internet sites, and I compared what I did, this one, and as you can see, they are similar. So that verifies my assertion for the movement of the graph of the speed versus the stopping distance. And these are also from other websites, and I have observed that my assertion is similar to those presented by these graphs. So that is the answer for this question, stopping distance problem. So as you can see, we noted or we described our function in terms of words. This is an example where words are given, and we explain them or we answer them using graphs and domain and range. Okay, so this is the end of my lecture for lesson 1, and I hope you enjoyed the lecture, and thank you for listening and watching. This is Mr. Ron, your guide in Precalculus. Thank you and goodbye.